Today we're going to have a look at powers and roots of complex numbers. Almost wrote poots. Powers and roots of complex numbers. And, specifically, this is Demoivre, Demoivre theorem. Now, in mathematics, throughout all of mathematics, there's not a whole lot of theorems that have a person's name attributed to them. It's a pretty big deal. Demoivre's theorem, Pythagoras' theorem, that's the Pythagorean theorem. It's named after Pythagoras, the Greek mathematician. Euler's theorem, named after Leonhard Euler, Swiss mathematician. There's not a whole lot of them, okay? Fermat, I think he has one or two. Fermat, another French guy. But Demoivre's theorem is, it's really a very important theorem in complex analysis. And it deals with taking the powers and roots of complex numbers. So here's Demoivre's theorem. It's already on the board on our anchor chart up here. But if we have a complex number in polar form, r cosine of theta plus I times the sine of theta, and we raise that to a power, n, that n can be any rational number. It may work for irrational numbers. I haven't really put that theory to the test. I don't know the intricacies behind what n has to be. The solution to this is r to the n power cosine of n times theta plus I times the sine of n times theta. So you raise the radius to the power of n, and you multiply the angles by n. You getting this, Bryce? Doesn't it look like you have a notebook out? Somebody loan poor boy something to write with and a piece of paper. This is a big deal. Today's lesson is a big deal. Okay? It's a tough lesson when you're on your game, so we need everybody on their game today. Here's an example of what this would look like. If we take 2 cosine of pi over 3 plus I sine of pi over 3, and we raise this number to the 5th power. Let me rewrite that. That's kind of sloppy. I got lost with my parentheses in there. 2 cosine of pi over 3 plus I sine of pi over 3 raised to the 5th power. There we go. I'm just going to apply the theorem there. So what are we going to do with the 2? The radius of the complex number, we're going to raise it to the 5th power, right? And I'm going to take the angles and multiply them by 5. So this will be cosine of 5 pi over 3 plus I sine of 5 pi over 3. All right, 2 to the 5th is 32. Cosine of 5 pi over 3 is 1/2. Straight out of your unit circle, or hopefully some of this is now starting to come straight out of your head. The sine of 5 pi over 3 is negative square root of 3 over 2. And so that's 16 minus 16 square root of 3. Okay? Do what? 5 pi over 3 is in the 4th quadrant. So cosine is positive, sine is negative. Yes, absolutely. We have to have an I. I'm sorry. We've got to have the I. It's a complex number, right? 16 minus 16 square root of 3 I times I. I would prefer that to be 16I times the square root of 3 if you haven't written it already, just to make sure that we know where that complex number is not under the square root. It's not a 3I. The I is outside of the radical. Okay? Now, I want to show you what we've actually done here using Demoivre's theorem. If we take this original complex number, right, and we put it into rectangular form, we're done with the problem. But I want to show you what we've done. Cosine of pi over 3 is 1/2, right? 2 times 1/2 is 1. The sine of pi over 3 is the square root of 3 over 2 times 2. That's the square root of 3. So our original problem was 1 plus I times the square root of 3 raised to the 5th power. And it is equal to that. So what Demoivre's theorem has done is given us an alternative to taking a complex number and expanding it. 1 plus I times the square root of 3 to the 5th power means 1 plus I times the square root of 3 5 times. So if I wanted to do this algebraically, I would need to do this 1 plus I times the square root of 3 times 1 plus I times the square root of 3, etc. 5 times, right? Demoivre's theorem gives us a shortcut to doing that algebraically. And so the larger the number, the larger the power is, the greater shortcut we have in actually doing this. All right? Everybody okay with that? All right, so let's look at a next example. Let's start with a number that's not in complex form, or excuse me, not in polar form. For our next example, let's look at 1 plus I raised to the 6th power. 1 plus I raised to the 6th power. Now, what would that look like algebraically? 1 plus I times 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 1 plus I. That's a lot of multiplication, right? Even if you use Pascal's triangle, you could go down to the 6th row for 6th power of Pascal's triangle and do all of your coefficients there. I to the 6th, blah, blah, 1 to the 6th. You'd have a lot of powers of I to simplify and collapse. It's still not a fun process because every standard form, every complex number operation, we have to reduce it to A plus BI form. Right? So the most efficient way to do this problem is to convert the number to polar form and then use Demoivre's theorem to raise it to a power. All right, so step number 1 is to convert this number to polar form. Let's kind of remind ourselves what that looks like. Polar form of 1 plus I. 1 plus I is in the first quadrant. It's 1 on the real axis, 1 on the imaginary axis. This is going back to last Thursday's homework where we're writing the number in polar form. So we need to know the radius of the number, and we need to know the angle of direction. The radius is equal to the square root of a squared plus b squared. So the radius is equal to the square root of 2. Right? Theta is the inverse tangent of b over a. Inverse tangent of 1 over 1 is what? Pi over 4 in the first quadrant, so it's just pi over 4. All right, so this complex number in polar form is the square root of 2 times cosine of pi over 4 plus I times the sine of pi over 4. And we're raising that to the 6th power. Okay? Is everybody with me?
How'd you get the square root of 2?
The radius of the number. It's the absolute value. Right? Square root of 1 squared plus 1 squared, which is square root of 2. All right? Step by step. So if you look at the anchor chart here, guys, what we're doing today is starting with a number in standard form. We're going to find its radius. We're going to write it in polar form, and then we're going to use Demoivre's theorem at the end here. So we really have to have an understanding of everything along the way. This is a culmination lesson of sorts, what we've done over the last 4 lessons in class. This uses all the skills in a single problem. Now, are we ready? Now we'll apply Demoivre's theorem, which says we need to take the square root of 2 and raise it to the 6th power. Now, you could do that in your calculator if you would like. I'd like for you to be able to do it here. All right? The square root of 2 is 2 to the 1/2. 1/2 raised to the 6th power makes that 2 to the 3rd, which is going to be 8. And what do we do with the angle in Demoivre's theorem? You multiply 6 times the angle. 6 times pi over 4 is 6 pi over 4, which is going to simplify to 3 pi over 2. Plus I times the sine of 3 pi over 2. Let's put this in a plus bi form, standard form, or rectangular form we call it. The cosine of 3 pi over 2 is 0. Right? From your unit circle, cosine of 3 pi over 2 is 0. So this is 8 times 0 minus 1i, which is negative 8i. Okay, so our original problem up here that we started with, 1 plus I raised to the 6th power, reduces all the way down to negative 8i when you expand it and get all your powers of I simplified. Now that's an extreme shortcut in the process of expanding that number. Demoivre did us a favor when he discovered this. If you ever have to do this ever again anywhere else past this next test. Those of you who are going into math fields, chemical engineering, space science, you'll do this kind of stuff again. You'll see this again. All right? Any questions on this? All right, let's do one that is not as friendly to work with. Let's do Y'all with me? Let's do next example. One minus 2I to the 5th power. One minus 2I to the 5th power. Now, the reason that this one is not going to be as friendly is because it is it's not a first quadrant angle, for one thing, or first quadrant number. It's also not going to be a special angle. It's not going to be pi over 6 or pi over 4 or pi over 3. This is an angle that's going to be, we're just going to put it in degrees and roll on. All right, so 1, negative 2 is 1 to the right, down 2 in the complex plane. What's the radius of the number? Absolute value of the number is what? Bryce? Elizabeth? Square root of 5 is correct. 1 squared plus 2 squared is 5. So my radius is the square root of 5. Okay? My angle is the inverse tangent of negative 2 over 1. What does that give us? Should be a negative angle, right? Say it out loud. Give me 3 decimal places. Negative 63.435 degrees. That's what I'm going to use. I'm going to use the negative angle. You could add 360 to that to get the positive angle, but let's just use negative 63.435. It works. Theta doesn't have to be a positive angle. So now I'm ready to write this in a polar form. This number is equal to the square root of 5 times cosine of negative 63 point what? 435 degrees plus I sine of negative 63.435 degrees, and we're raising this all to the 5th power. Now we're just going to go into decimal world here, right? When things don't work out nice and we don't have nice, pretty fractions to work with, we're going to go into decimal world, and we're going to keep 3 to 4 decimal places so we can get some good accuracy at the end. What would we? Plus I sine of? Yes, always. R cosine theta plus I sine of theta. It changes signs based on the angle that's in the sign, so sometimes it'll become negative because we're in a whatever quadrant we're in. All right, so then what do we do here? The square root of 5 raised to the 5th power. It's 5 to the 2.5 power. Is that right? What do you get when you raise 5 to the 2.5 power? Or square root of 5 raised to the 5th power. What'd you get, Elizabeth? 55.9. Is that accurate to how many decimal places? Well, let's try it. 55.9. We'll keep just one place there. That's good enough. Times cosine of 63.435, negative 63.435 times 5. What do we get? What do you get? Negative 317.175 degrees. Okay, we got another one of those, right? I times the sine of 317.175 degrees. All this is being raised to the... No, we just did the fifth power, so I'm good. Yes, it is. Thank you. Forgot the negative. That makes a big difference, right? It may not actually, because 317 degrees and negative 317 degrees are both in the first quadrant, but you still need to be careful with it. Now it becomes a calculator game, right? 55.9 times cosine of negative 317.175 degrees gives us what? What do you get, Elizabeth? 40.99. 40.99, we're going to call that 41. And then 55.9 times the sine of negative 317.175 degrees is we got to hurry. What do you get? How many? 38. 38i. .000 or something like that. 37.998. Yeah. Then the reason we round that is because we wouldn't expect to have decimals, right? Because the only things we're multiplying in our original problems are 1s and 2s. So when that expands, it's going to have integral values. So you keep a bunch of decimal places in your problem, and then you round to the nearest whole number at the end. Okay? So that's 41 plus 38i. That's what you would get if you multiplied 1 minus 2i times itself 5 times. And the chances of multiplying that out and getting all the i's collapsed correctly and not making any kind of arithmetic mistakes along the way are pretty slim if you're doing that expansion. Okay, so Demoivre's theorem really helps us. Now, the main thing that we really love Demoivre's theorem for is that it gives us a way to find all the roots of a number as well. So if we started with, in algebra, we had this equation, x cubed plus 1 equals 0. That means x cubed equals negative 1, and that means x is equal to the cube root of negative 1, right? The cube root of negative 1 is negative 1. What's the problem with that process? What's the problem with that process? How many solutions does x cubed equals negative 1 have? According to the fundamental theorem of algebra, how many solutions are there? 3. And I've been telling you all year long that there's 2 square roots to every number. Every number has 3 cube roots. Every number has 4 fourth roots. Every number has 5 fifth roots. And every number has n nth roots. And the process of finding those roots is Demoivre's theorem. Okay, that's one of the processes we would use. This one we could actually apply an algebraic process. But I want to use Demoivre's theorem to find all 3 cube roots of negative 1. All right, so we're going to use Demoivre's theorem to find all 3 cube roots of negative 1. If I'm going to use Demoivre's theorem, I need this number to be in what form? Polar form, right? So let's talk about -1 in polar form. -1 is over here on the real axis. It has a radius value of 1. What's the angle that goes with that? What's the angle? 180, let's put it in radians. Pi radians. The reason we want it in radians is because, well, you could use the other one, but you'll see why in just a second. All right, so -1, the cube root of -1 is the same as -1 to the 1/3 power, which is the same as 1 times the cosine of pi plus I sine of pi raised to the 1/3 power. All right, now this is going to give me my first solution. How many solutions are there? 3. All right. So when we apply Demoivre's theorem, 1 to the 1/3 power is 1. Cosine pi times 1/3 is pi over 3. Sine of pi times 1/3 is pi over 3. And that's pretty easy. I can finish that off. Cosine of pi over 3 is 1/2. Sine of pi over 3 is square root of 3 over 2. So there is one of the cube roots of -1. If you cube this number, you get -1. All right? I don't have time to reason you through this, but I'm going to tell you how to find the others. How many are there? 3. So we're going to take our original reference angle, which was pi, and we're going to go all the way around again to get to it. What did I add if I go all the way around? 2 pi, right? So what's pi plus 2 pi? 3 pi. So the second solution, the second cube root of 1 to the 1/3, -1 to the 1/3 power is 1 times the cosine of, instead of pi, we're going to use 3 pi plus I times the sine of 3 pi. And we're raising that to the 1/3 power. Okay, so we use Demoivre's theorem again. 1 to the 1/3 power is 1. 3 pi times 1/3 is pi. Okay. Cosine of pi is -1. Sine of pi is 0. So this is equal to 1 times -1 plus 0. It's equal to -1. That's my real solution. Now how are we going to pick up that third solution? We're going to add 2 pi again. What's 3 pi plus 2 pi? Y'all with me? 3 pi plus 2 pi is 5 pi. One to the 1/3 power is 1. 5 pi times 1/3 is 5 pi over 3. Cosine of 5 pi over 3 is 1/2 again. Sine of pi over 3 is negative square root of 3 over 2 times I, or I times the square root of 3 over 2. Now what we have found here is the 3 cube roots of -1. These are also the 3 solutions to x cubed plus 1 equals 0. All 3 solutions, which we actually found algebraically back in college algebra. Okay, so somebody tell me the process of what this looks like. Write the number in polar form. Find the first representation of it. How we find the other roots? You add 2 pi to that angle, you add 2 pi to that angle again. We're not going to have time to finish this problem, and maybe you guys can just put down a pencil, and this will be online if you want to speed through and look at it. But let's look real quickly at the 4th roots of -I. 4th roots of -I. How many 4th roots are there? How many 4th roots does -I have? Every number has 4 4th roots. Just like every number has 2 square roots. Start by writing it in polar form. Okay, the polar form of -I is down here, right? -I is down 1 on the imaginary axis. So it has a radius of 1, and it has an angle of what? 3 pi over 2. So this is equal to, the first solution is going to come from 1 times cosine of 3 pi over 2 plus I times the sine of 3 pi over 2, and we are taking the 4th root of that number. Now that's going to give us an unfriendly number. Cosine of 3 pi over 8 plus I times the sine of 3 pi over 8. We could get a decimal approximation for that number, but that's not one of our special angles, so we're just going to leave it alone. Where's the second solution going to come from? Take 3 pi over 2 and add 2 pi. 2 pi is 4 pi over 2. So it would be cosine of 7 pi over 2 plus I sine of 7 pi over 2 raised to the 1/4 power. 1 to the 1/4 is 1. Cosine of 7 pi over 8 plus I times the sine of 7 pi over 8. All right, there's my second root. Do you see a pattern? What do you think the third root that we would find would be? 3 pi over 8, 7 pi over 8, 11 pi over 8 would be the next one. The next one would be 15 pi over 8. So there's patterns that emerge in most of these that you would be able to find. Okay? So those are polar form answers. If you wanted a decimal approximation from that, you could use your calculator to get it. Okay, so that's Demoivre's theorem, 2018.